Alright, we are going to start the work energy theorem today. This is lecture 37 and 38 of this course. So the work energy theorem is one single scalar equation that relates work done by forces on work done by all the external forces on an RB on one side and change in its kinetic energy of the rigid body on the other. Now keep in mind that the work energy theorem, which we will derive in a little while, is not a new equation. It's not an independent equation. In context of the two equations that we already have, Euler's first equation, axiom and Euler's second axiom are already there in the background. The work energy theorem is somehow a combination of those two equations. So that is what I mean. It is not a new equation. It's a combination of the two Euler's axioms that we are already aware of. Then the question is, why do we bother about combining the Euler's first and second axiom and getting what we want to call as the work energy theorem? What is the motivation? The motivation is that having one scalar equation is useful in some situations to find one scalar directly. Right? So if you are given a problem, you have to solve for one unknown. It turns out that in some situations, if you use the work energy theorem directly, you will use less algebra to get the solution. Sometimes you also do not have to worry about some of the forces that might be acting on the RB. Now, if you are using Euler's first and the second axioms, you will have to take into account all the forces, external forces that are acting. It turns out that if you use the work energy theorem, some forces need not be accounted for, and still you will get the value of one scalar that you are chasing. Okay, so there are some advantages of being aware of the work energy theorem. And these advantages will become more clear as I derive the work energy theorem and also later when I try to solve some problems, example problems. So I will show you the work energy theorem, the expression. I will also derive it. But before we reach there, before we get the actual theorem, there are some new quantities that need to be defined. Like the rate at which the external force system does work on an RB. Rate at which external forces do work on an RB. So I'm talking about work done by a force. Actually, this is not a new quantity altogether for you. You must have come across this phrase, work done by a force, but on a particle. That's what my guess is. Earlier you might have seen rate at which work is done. Rishabh.
Yeah, have you started?
Yeah, that's what I have started.
No, your sound is not audible. I think you're on mute, sir.
Alright, okay.
Yeah,
I realized it.
Yeah, now your sound is audible.
Okay. Alright. So I want to first derive an expression for the rate at which the external force system does work on an RB. So let's consider an RB which is having its center of mass here, and there are n external forces acting on it. There is a reference frame F. Okay. We define a new quantity, at least in context of RBs, as PF. And this I call as the rate at which all external forces are doing work in an RB. It's defined as this. Now this quantity is a scalar, it's not a vector, but depends on frame. Why it is a scalar, that must be clear, because I have a vector here and there is another vector. We are taking dot product, and then we are adding several such dot products. So of course the resultant quantity will be a scalar. But why is this a frame dependent quantity? In fact, to highlight that, I have used this symbol P bar F. Why is it frame dependent? Is the frame dependence coming because of Fi? No, this is not frame dependent. All forces in this course are real. We never talk about pseudo forces. Yes, if one starts talking about pseudo forces, then one would say that yes, that force also depends on the reference frame. Not in this course. Whenever there is a talk about a force, that force has got to be real. So this and those real forces we are saying are not frame dependent. So why would P, this quantity, depend on frame after all? The frame dependence is coming because of this quantity VIF, which is the velocity of the ith of the velocity of the location where the ith force is acting. VIF is that with respect to F. So this VIF vector is frame dependent, and thus in general the dot products here will be frame dependent, and that is why this PF quantity, the rate at which all forces are doing work on RB, is also frame dependent. The units of this will be Newton meters or joules, SI unit. Rather, it is a rate at which, so I should say Newton meter per second, joules per second, because it is a rate. You can also say watts. Now, as I move towards the work energy theorem, I would like to prove a relationship. The relationship that is shown in the yellow box on the screen. What it is telling us? It is telling us that rate at which all forces do work on a rigid body, that can be written as velocity of the center of mass of the body with respect to frame F Now note that this reference frame F that I have been talking about is a general reference frame. No restriction on this. Also, I want to mention that F is being used for many things here. The letter alphabet, the capital alphabet F is being used for many things, but it should be clear from the context what we mean by that. So if F is just being used without an underbar, it means a reference frame. If I put F like this, then I mean to say it is a force vector, and then I am also putting Fi, and that means the ith force vector. So even though F is being used in all three symbols here, but you can see there are differences, and those differences will keep the meaning unambiguous. Now in this equation that I want to prove, VCF is the velocity of the center of mass, Cm of Rb with respect to F, right? And then F appears here with a vector or with an underline. And what does this mean? This means the net external force on the Rb. And omega mf is the angular velocity of Rb with respect to F. And mc is the net moment due to all external forces. All external forces. Due to the entire external force system. About C. Now if there are n forces acting, all forces included, whether they are couple, non-couple, I have included all of them in n, in this set of n forces. Then F is basically summation of Fi, I going from 1 to n, and MC will be RIC crossed with Fi, summation I 1 to n. This is location 1, this is location I, this is location n. Okay, let's prove it. According to the definition of rate at which work is being done on the previous slide, I defined this quantity as right. Now next time onwards, whenever I write the summation symbol, I will not put the indices. I will not put I equals 1 to n. It is implied. It will save me some time and effort. Now let's call this equation 1. But then we realize that I can write VIF as this. Right? I have used VTR, velocity transfer relationship, with IF being M and IP being C. Let's put it here. Now, if you pay attention to this summation, you will realize that VCF is a constant for that summation. You go from I equals 1 to n, Fi keeps changing, but VCF is not dependent on the index I, and thus I can pull that out of the summation and write this as simply this. Now this is the net force on the RB, and I am going to write it as F dot VCF. Let's look at this expression. If you focus on what is inside, it seems like we are taking the cross product between two vectors, let's call them B and C, and then the resultant thing is being dotted, or the dot product is being taken with another vector A. That is the form of the expression there. Now there is an identity that if you have an expression like this and you change the order of A, B, C, you make A as B and then B becomes C according to this kind of thumb rule that I have made here. A becomes B, B becomes C, and C becomes A. The expression remains unchanged, and thus I can write this second expression as inside the summation itself. Okay. After doing this, I realized that this quantity is not dependent on I. So I can safely pull this out of the summation, and then I have this dotted with RIC cross FI. Go back to the previous slide and note that this summation RIC cross Fi, I going from 1 to n, that is what we call as MC, and that is the net moment due to the entire force system. So I'm going to bring back that symbol and I get this. So I have proved it, proved a useful expression. What that useful expression is? If you want to find the net rate at which work is being done by a force system on an RB, you can either do summation like this, alternatively you can find the same quantity taking two dot products only, and the two dot products would be such that the first one has the net force, not the individual force, but the net force being dotted with velocity of center of mass of the RB with respect to F. And the second expression is the angular velocity dotted with the net moment due to the entire force system acting on body, on the RB. Okay. Now let us define the kinetic energy of an RB with respect to F. Last two slides I defined the rate at which external force system does work on the RB. I got a convenient expression for that. Now I am defining a new quantity, kinetic energy of an RB with respect to F. Now if you have an isolated particle of mass m, we are aware that the kinetic energy of particle, let's call it particle Q, here with mass m, with mass say Qm, rather mq, with respect to F. Now you must be aware of the definition of kinetic energy for a particle, but I don't know how many times you paid attention to the fact that even for a particle the kinetic energy actually is frame dependent. So this phrase is required. This will be the kinetic energy of the particle. So since there is a velocity involved, the frame automatically becomes relevant. So the same particle will have different kinetic energies with respect to different frames. So this is about a particle. My focus is kinetic energy of an RB, rigid body, with respect to frame F. Kinetic energy of an RB with respect to F. I am going to use this symbol T bar F. Ft means kinetic energy, T symbolizes kinetic energy, F symbolizes the significance of with respect to which frame. How is it defined? Defined like this. Integral over the whole body. What is VPF? So this is body M. P is a typical particle, typical point on the RB. This is frame F. Okay. Now based on these two definitions, P with respect to F, T with respect to F. One more thing I want to point out, of course this is also a scalar. Kinetic energy is clearly a scalar. There is a dot product between two vectors, but it is frame dependent. And the units would be Newton meter or joules. So having defined rate of change, rate at which work is being done on one hand, and the kinetic energy of an RB, here is the work energy relationship. The work energy relationship says that the rate at which the external force system is doing work on an RB with respect to an inertial reference frame equals rate of change of kinetic energy with respect to the same inertial reference frame. Now mind you, whatever I did so far in today's class, the reference frame was F. F, no restriction. You can define kinetic energy with respect to any frame of your choice. You can define rate at which work is being done by all forces with respect to any frame of your choice. However, the relationship that exists between the rate at which work is being done on one hand and the rate at which kinetic energy is changing on the other hand, for that relationship to exist, keep in mind that the frame must be inertial. If the frame is not inertial, there is no work energy theorem in general. I would like to prove it. We will solve some problems also, but not without proving this. We will prove it first. So recall from the previous slide the definition of T with respect to any frame F. Recall I said this is how we define kinetic energy of an RB with respect to frame F, and if it is T with respect to I, you just have to change all F to I. Where P is a typical point, C is the center of mass. Let's write VPI as adding subtracting VCI substitute VPI from 2 in 1. I am trying to prove this. So first I am trying to write a different kind of expression for T with respect to I, such that it takes me closer to what the expression that I derived earlier for P with respect to I. So it involves some particular steps. We have to go through this procedure. Okay. Let's have 4 different integrals. Four terms, 4 different integrals. Two of them are actually the same. Look at this. Same. Half and half will add up and it will become 1 time of what you see in those integrals. On the other hand, you see this VCI doesn't bother about the point, typical point P. It's really a constant for the integration process, and thus it can be pulled out, and once it is pulled out, what will be left inside the integration process will be just dm, which when integrated will give you the total mass of the RB. So the first term is going to be m by 2 VCI, and these two terms will be added together and they will become VPCI dotted with VCI DM, and then there is one more term let's call it 1, 2, 3. Actually this one doesn't need any processing, so does not need any further processing, so I am just going to work on this. Let me call this B, let me call this C, just the expressions. B, let's work on B. VPCI, VCI. We have seen this kind of expression before actually. This kind of will become clear in a little while. So my claim is that VCI is a constant for integration. Inside the integration you simply have VPCDM. Have we seen anything like this before? Yes. When we were deriving the modified Euler second axiom, we came across such an expression. VPCDM this term VPCDM can be written as VPIDM will turn out to be M times VCI, and VCI here itself is a constant. It will be out of the integration, leaving integral of dm, which will become MVCI again, equals 0. Okay. You're left with term C. Okay. So I'm going to take it forward. I'm going to take the expression of Ti as this plus this. So let's take the derivative of it. Observer is fixed to frame F. do I get? I get d dt t of I n by 2 okay, with respect to I. Now t of I, t with respect to I is a scalar. Whether I put I or I don't put I, it really doesn't matter. So I will just leave it as this. But here I would keep I because I am going to take this derivative operator inside the parenthesis here and here. And as I take the time derivative inside the parenthesis, I will let the time derivative act on individual vectors. And the moment I let a time derivative act on an individual vector, it becomes important, in fact mandatory, for me to specify the time rate of change of a vector with respect to which frame I am talking about. Right? And that is why the right hand side, this was equal, right hand side I get 2 times of d dt vci I dotted with vci, right? And I get again 2 times of integration this is what you get. Okay. Now the time derivative of vci with respect to I is nothing but acceleration of c with respect to I. Okay. And here I leave the terms as they are for the time being. Okay. And now look at this product here, MACI. What is that? According to Euler's first axiom, tells me that this must be net force, right? Net force. Recall, I am in the process of deriving the work energy theorem and I have used the Euler's first axiom. It means that the work energy theorem is going to be dependent on this equation, Euler's first axiom, which is fine. I said it in the beginning itself that work energy theorem is a sort of combination of Euler's first axiom and second axiom. Also keep in mind that had I not taken this frame to be I, if this frame was F, MACF, I cannot replace MACF with F alone. For that to be true, the frame has to be inertial. And that signifies why I said earlier that for this to be true, the frame has to be an inertial reference frame. All these things are important. I believe they are very important. The derivation may be boring, I agree. Problem solving may be exciting, I agree. But all problem solving is done based on these derivations, and that's why I attach a lot of importance going over these derivations. In fact, most of my class I spend time deriving. Alright, so first expression I have handled. Let me call this as d, and I will process that on the next slide. So d dt of t with respect to I have derived this much, half the work I have done. Now let's look at d. What is d? VPCI as omega mi cross RPC. Okay. So d becomes also note that this quantity here can be written as APCI. PCI is AI API minus ACI. Again, I have a situation like A dotted with the cross product of B and C, and I would like to change the order of these things. Why I do that? Because I want to pull out whatever is constant over the integration. So I'm going to write this as omega mi dotted crossed with RPC crossed with APCI dm. Did omega mi can be brought out. Okay. RPC cross APCI. Now at this point, let me add this extra term here. This is 0 actually. So adding, subtracting, not adding doesn't matter. Cross product of any vector with itself is always 0, and that's why I am allowed to add it. How does it help me? I'm putting back this. In a way, this was not required actually to put APCI. I could have worked with DDT or BPCI also, but that's fine. Here I'm going to take some help with this new expression. I can write it like this. The second one is important. I have written it in an alternate format, right? This VPC can be written as this DDT RPCI. How does it help me? It helps me because now you see, if you apply product rule of differentiation, what you actually have is ddt of RPC crossed with VPCI dm. That's what is inside the integral. And then we realize that, and of course there is I here with respect to I can write this as ddt of integral of RPC cross VPC, the whole integral being differentiated with respect to I. Are we familiar with this term? Are we familiar with what is inside this integral? Are we familiar with what this is? Indeed, that is HCI. So I have D as omega mi dotted with d dt of HCI with respect to I. HCI is the angular momentum of the RB about its own center of mass and with respect to frame I. It's quite a journey, quite a derivation. D becomes omega mi dotted with d dt of HCI. So let's take back D. Let's rewind the tape. D will be plugged in here. I already have F dot VCI, and that must be the rate of change of kinetic energy with respect to frame I. So I'm going to assemble these terms. Let's call it star here, and I call this double star here. I'm going to take D from double star, previous slide, and plug that into single star. What do we get? We will get d dt of Ti equals first term F dot VCI plus omega mi dotted with HCI. Let's call this triple star. Now recall on slide number 4, what did I derive? Based entirely on the definition of rate at which the various forces do work on the RB, I derived this, where the frame is F, but of course it is true for any frame F. I can always choose a F to be I, special case. And once you put F equals I, the frame F equals I, you will get F dot VCI plus omega Mi dot MC, right? Let's call it 4 star, slide 4. I'll give a break, let me complete this derivation. I want to get done with it. Now recall triples 4 stars, slide 4. What was that? That was PF equals F dot VCF plus omega MF dot MC. Set F equals I. Always, we can always do that. I get PI equals net force VCI plus omega Mi dotted with what? Dotted with MC. But Euler's second axiom, in fact MESA, modified Euler's second axiom about center of mass. What does it give us? It gives us this. Right? Therefore, P with respect to I is F dot VCI plus omega Mi t dt of SCI with respect to I. Now compare this 5 star with 3 star. 5 star is the same as 3 star. Except that I forgot this symbol. This has to be there. I forgot to put it here. This must have been HCI. They are the same. And thus I have proven that Pi equals d dt of Pi. This is the work energy theorem, WE theorem. Rate at which all external forces do work on the rigid body with respect to I equals the rate at which the total kinetic energy of the RB is changing with respect to I. We are done with this derivation. Alright, we will take a break. We meet at 10 past 5.